Hello, chemist. Jolly here. This is the second portion of the review of the first semester of organic, and we are going to be talking about the halogens and the oxygen reactions. So we finished up the hydrocarbons. All right, let's talk about these halogens. All right, so our alkyl halides, again, we can be very specific and say primary, secondary, tertiary. There can't be a quaternary, okay, because it has to have one bond to the halogen. What about the reactivity? Okay, now I wanted to point out, I put a no right there, even though there are lone pairs. Keep in mind the halogens don't like to become positive, so normally it won't use its lone pairs unless it's all by itself. They're better at leaving groups in this case. So, yes, it's a leaving group. So let me show you the difference between the two. If I wanted to make it be a nucleophile, sad. Okay, it's not going to want to do that. It would rather break the bonds right here. It would rather break that bond as a leaving group. All right, well, how about acid and base? The hydrogens here are very, very strong. So hydrogen, they don't like to come off, and that goes back to the acid-base chapter. All right, so we don't have to worry about them really as nucleophiles. We don't really have to worry about them as acid-base chemistry. So the only thing we need and their power is that they are leaving groups. So what are our reactions that use leaving groups? Substitution, and if that nucleophile is very strong, we would call it elimination. Okay, so you can have SN2 or SN1. Okay, now that depends on the structure of your substrate, of your alkyl halide. Again, the Jolly simplification rules says that methyl, primary, and secondary prefer SN2, and that tertiary, allylic, and benzylic, that's a B, prefer SN1. Remember, that's a simplification rule. When you get in the middle, those secondaries, they can go either way. And then the allylics and benzylics, you also have to look at the whole molecule. All right. Well, what about the solubility? At least these molecules are polar, okay? But they can't hydrogen bond with the water. So yes, I know they're polar, but most of the time they are not soluble. In fact, we use some of the alkyl halides to dissolve organic or nonpolar compounds. Okay, other names they're known by haloalkanes, and if it's on a double bond, you can call it a vinyl halide. Look how short that was. All right, now this one is probably the most frustrating set of reactions to do because this literally goes back to the SN1, SN2. Of all of them that I'm reviewing, I don't want to say it's the least important, but it's probably the last thing that you would go and really, jump in depth into. Okay, as long as you have the basics of SN1, SN2, E1, and E2, you're golden. Okay, so this one, if you'll notice, has three different halides on it because I wanted one molecule to be an example for each one. So don't get frustrated if you look at the answer key on that one and go, oh, I didn't think to do both of them. Okay, as long as you get the general picture. All right, take home message. Alkyl halides, their purpose is a good leaving group. Okay, in a nutshell. What kind of reactions can you do with good leaving groups? Normally you do substitution and elimination. Nucleophiles can do two things. They can rip off hydrogens, okay, or they can attack carbons. So it has one of each. All right, oxygen. Woohoo. Okay, now oxygen's getting into more important territory. Okay, we have the alcohols, we have the ethers, and then of course we have the carbonyl containing. This semester we're going to go into depth for all the carbonyl containing. So just a brief review on the alcohols and the ethers. The alcohols may not be on an sp2 hybridized? No. Okay, because that really is a carbonyl in disguise. That's called ketoenol tautomerization. So what do we like about these alcohols? Can they be nucleophiles? Absolutely. The lone pair loves to be a nucleophile. Can it be an electrophile? No, unless we can convert alcohols into good leaving groups. And if that's true, then it could be a good electrophile. And can it do acid-base chemistry? You bet. Okay, it has a partially acidic proton. So let's just look at deprotonation. If I have an alcohol, now keep in mind, I would have to use a base that was equal or stronger to it. But yes, I could rip off that hydrogen and I could make an alk oxide. Alk oxide. Ide meaning negative. Oxygen because it's the atom oxygen and it's connected to an alkyl group. Okay, so yes, we can make strong bases using a strong base. Seems counterintuitive, but sometimes you have to use one to make the other one. So yes, you can deprotonate them as long as the base is strong enough to rip off the hydrogen. And remember, they have pKa's around 16 to 18. All right, well, you can rip their hydrogens off. Can we put hydrogens on? Sure. This one's really easy. This is called protonation. And yeah, for simplicity's sake, I'm going to put an H plus there. But remember, with the strength, it can rip off any hydrogen that is within its realm of that pKa 16 to 18. And you would turn it into a good leaving group. Okay, so anytime you throw acid in the presence of alcohols, even dilute acid, you are protonating those lone pairs and you have the potential of turning it into a really good leaving group. So if that's what you'd like, awesome. If you don't want that to happen, maybe don't use alcohols under acidic conditions. All right, we saw the oxidation in the oxidation reduction chapter. So if you have a primary, first, you can double up the bond, and it does have a hydrogen to give. So then you will end with a carboxylic acid. If it is a secondary, you would go to just a ketone. There's no hydrogen to give, so that's where you're done. Can you stop at this stage? Yes, if you use a selective oxidizing agent. Okay, how about this good leaving group issue? Okay, now granted, I just said that this alcohol, this protonated alcohol, alkyl oxonium ion, guess I should write that. Alkyl oxonium ion, that means it's positively charged. Yes, that is a good leaving group. But when you play with the acids, do you see anything that would be attracted to the carbon would also be attracted to the proton? So maybe that's not the best way to make it into a good leaving group. And so we're going to use a protecting group. These are the sulfonates. And I'll go to the reference sheet in a moment and show them to you. But generically, let me see how much room I've got. Not, so I'm going to go over to the whiteboard. All right, when you've got your alcohols, yes, you could protonate it. Okay, so that's one way to make a good leaving group. Another way is, and I'm just going to do generic here. Most of them have benzene in it. Oh, I can't remember if there's an oxygen there. All right, doing that off the top of my head, but there could be an oxygen right here in some variations. But the key is this is okay, that's a built-in good leaving group. Okay, that's a polar pi bond. So the oxygen is going to attack that. It's going to kick that up and it's going to say, hey, what are you kicking me out for? Reform, kick out the one that will actually leave, and we are left. And you know, I'll put an R on that. Okay. Now again, there could be an oxygen right there. This can deprotonate in case somebody's going to come along and it's going to deprotonate it. This is now a good leaving group. That is a good leaving group. So if you want to convert an alcohol into a good leaving group, you can use, yes, an acid, not the best way, or you can use the sulfonates. And then they each have different attachments and they have different name. So tosylate, mesylate, mesylate, triflate, triflate. Okay, that's the best leaving group. Again, probably don't care what it is attached to, just that's the idea. Okay. And last but not least, let's protect these alcohols. Well, why in the world would an alcohol need protection? Well, because remember that hydrogen is acidic and it actually can be ripped off. So if you don't want that to happen, you better protect it first. And I gave you one way, TBDMS chloride, tetrabutyl dimethylsilane chloride. Okay, that was a mouthful. Same thing. OTBDMS. Somebody will come along and deprotonate that. This is now protected. Go do whatever reaction you need to have done, and then you can take it off with tetrabutyl ammonium fluoride, and it will go back to the alcohol you started with. Okay, and so that is literally just a protecting group if you don't want the alcohol's hydrogen to react and do things unexpected. All right, let's go to the, nope, right here. All right, so on this page, okay, this is in your reference sheet, right there. This is the tosyl, but you could also use tosylate, mesylate, and triflate. Those literally are just converting to a good leaving group. Well, what about just strong acid? Yes, but, okay, it's under an acidic condition. You know, what's to say that that water won't pop off and make a carbocation? Okay, just a lot of times you don't want to be throwing acid at alcohols. All right, what is another reaction that you can do with the alcohols? Well, if you put it in the presence of strong acid and heat, you're going to get acid catalyzed dehydration. And remember, primaries are hard, so they have to have harsh conditions. Secondaries are somewhere in the middle, the fence sitters, medium, and the tertiaries are very mild. Okay. And again, they go through different mechanisms at first. So these two are E1. This one's E2. Oh, E1 goes through a carbocation. Watch out for rearrangements, so forth and so on. But in all cases, you're going to get alkenes and water, okay, because the water is actually going to come off. So let's just do a secondary. All right, the first step for secondaries and tertiaries is protonation. Oh, look, I have a good leaving group. And then whatever acid you use, its conjugate partner will then come and rip off. But remember, there's still acid and water floating around, so it's always in competition with addition. Make the alkene, break the alkene, make the alkene, break it. All right, what is the problem with this one? Possible rearrangements because you're using an acid. So is there a way we can dehydrate without an acid? And yes. We are going to do the same thing with POCl3 and pyridine. And it sees that wonderful pi bond, just has to break it, kicks it out. Oh, look, I just converted to a good leaving group. And then the pyridine is a base, will come along and rip off a beta hydrogen. Okay, but it's not under acidic conditions. All right, so those are your two ways to do dehydration. Now on mine, this shifted clear up here. This is supposed to be right there. So those two are dehydration. And here, what if you want to just convert it back to an alkyl halide? Okay, the answer for an alcohol is always convert it to a good leaving group and then attack it with whatever nucleophile you want. And in this case, if you want a chlorine, you're going to attack thionyl chloride. And if you want it to go back to a bromine, PBr3. So over here, oh look, those lone pairs just can't resist that polar pi bond. Hey, there's somebody you can kick out. What are you doing? There's your good leaving group. And then the chlorine sneaks in behind and kicks that out. Okay, so remember in our elimination and our substitution, you always have to look for what nucleophile is floating around. And in this case, it made its own nucleophile so that the chlorine can go back on. All right, this section, let me change some colors here. This section is the one that we just did in the oxidation reduction. So you can take the primary alcohol. If it's strong, it's not selective. You can use SWERN or PCC if you want it to be selective, but secondaries, you're stuck. Okay, secondaries go to ketones, no matter what, whether you use your selective reagents or not. Tertiary alcohols can't oxidize because they don't have a hydrogen to give. All right, here is your protecting. TBDMS chloride to put it on, TBAF it off, and then you're back with your original alcohol. All right. What is this other protecting group that I have right here? We actually didn't talk about that last semester because this functional group, an acid halide or an anhydride, actually come from this semester. So I'm going to show you it right here, but we will talk about it later. All right, so here's my alcohol plus an acid halide. Wow, this looks just like everything else I did. And you were right. Hey, what are you breaking me? Kick them out. Okay, somebody will come along. Okay, somebody will come along and deprotonate. This is now protected as an ester. If you want to get it off, okay, the other direction, you're going to add some acid and some water. You're going to hydrolyze it. Okay, so that is another protecting group for the alcohols. All right, the Williamson ether synthesis. This one is very interesting because we're going to make an ether using two alcohols. Okay, what in the world does that mean? Whoops, these two are backwards. That is the Williamson ether, and that is the acid catalyzed condensation. I don't know if your reference sheet has those backwards. This overhead is from a long time ago, so just make sure that you have those correct. And I'm going to have to go over to the whiteboard again because I write too big. All right, the Williamson ether. Not the best way to make an ether because there's very special conditions. Remember, when you have an RO minus, this is a strong base and it prefers elimination. but we're going to tweak our conditions so that, so for instance, let's say CH3X. There is no hydrogen to rip off for elimination, so the only thing it can do is make the ether. All right, so it manipulates conditions. Not really violating any rules, we're just manipulating. And the other one, the acid condensation, again, there's that word acid. Acid and alcohols are not the best synthetic methods. Condensation. Let's take CH3OH and let's put it in the presence of some acid. And the first thing you do is make a good leaving group. Surprise, surprise. But then guess what's also still floating around? It's a nucleophile too. Oh, look, I made an ether. And again, somebody will come and deprotonate. Water, something else. One of the alcohols, deprotonate. Okay, this one, again, not a really good way to make ethers, but technically it works. All right, so that takes care of this one and that one. Okay, and condensation means water does come off. All right, what is our next functional group? Those are our ethers. Ethers, they're very, you know what? I'm going to go back to the notes first before we do that. Oh, I was in the right spot. Okay. Sorry. So we're not going to go on to ethers. I'm going to finish out alcohols here. Ooh, solubility. Okay. Alcohols are polar and they can hydrogen bond. So it's going to depend on how large they get. And generically, if it can participate or hydrogen bond, okay, if it's 4 carbons or less, we're going to say 100% soluble, 5 to 6 partially, and greater than or equal to 7, we're going to say non-soluble. So remember that about alcohols. Okay, our ethers and our epoxides. Ethers, the main reason we have seen ethers in the past is because they can be polar, but they are not acidic. So they are great solvents. Okay, we love the ethers as solvents. Hey, can they be nucleophile? Well, yes, they have lone pairs on oxygen, but they do not have an acidic hydrogen. Okay, so you can't really rip them off, but you can easily protonate them. Okay, so they're just perfect solvents. Now, epoxide is a special one. It's a 3-membered ring, very strained. So already you have a built-in leaving group because that bond wants to break. All right, here is an example of the epoxide reaction, and then I'll go back and show you the ether one. All right, this one is less sterically hindered. This one is more sterically hindered. So if you have a nucleophile, we're going to go with sterics. It's going to go to the less sterically hindered side, and it's going to pop open. And then you're going to protonate. But, if you protonate first, okay, this is now more stable. So if you will, kind of like the polonium ion, the positive, okay, when the bond breaks, the positive would go to the most stable spot, and that is now the other carbon. And then your nucleophile now attacks that spot and kicks out. So this one is called base catalyzed, not because you'd use a strong base, but because you're just starting with a nucleophile. and this one is called acid catalyzed. And so you can control the regiochemistry based on it being protonated or not protonated. Well, not you. All right, so that one, acid catalyzed ring opening and base catalyzed ring opening. Okay, we just did those two. This is technically acid catalyzed ring opening, but your nucleophile is another alcohol. So you're going to end up with a glycol or a diol. And the halohydrin. Okay, so we've got the acid. This would get protonated. That would go to the most stable spot, and you would be left with, okay, that one would be a diol, okay? And it has to be anti because it came in from backside. The only difference between that and the halohydrin is your competing nucleophile is a halogen. So instead of the water right there, it would be a halogen. And so you would put a chlorine in that spot instead of an alcohol. So that takes care of our epoxide reactions. Well, what about ethers? Okay, it has a lone pair, so you can convert it into a good leaving group. And guess what? If you have an alcohol or water floating around, you'd kick off that good leaving group and you would go back to your alcohols. You would get back to your alcohols. Okay, that's called hydrolysis. So the same way, breaking the bonds with water and putting an H and an OH back in its place. And look, same thing with the HX. The only difference is you would use a halogen as the nucleophile. So you would end up with an alcohol and an alkyl halide. So not a lot of reactions for the ethers and the epoxides. And let me peek to the next. Okay, that one is for this semester. And I think everything past that. Yep. So that completes our review of everything that we covered in the first semester. Before I do leave, these, okay, are some of the solvents that we use in lab. I commonly use diethyl ether, and sometimes we use THF, but they're great because they're not acidic, and you can manipulate how many ethers for the polarity. And last but not least, here is your alcohol. Okay, so I gave you a primary alcohol and I gave you a secondary alcohol. And then for your ethers and epoxides, there weren't very many variations. So those are your practice problems for them. And that ends our review of the first semester. All right, again, I need a working understanding. You don't have to be perfect at it, but you can't just take an hour to go, oh, how would I get from this to this? And you have plenty of time. We have the whole first half of the semester to get all of our reactions in order. So don't feel like you have to do all of the review at the same time. Okay, but we will start new material in the next lecture. All right, until until next time, jolly out.